this video, I am introducing you to topics associated with these things or these objects, or really they're projectiles. They're referred to as satellites. A satellite is an object that follows an elliptical trajectory around a large gravitating mass. So, for example, our Earth is a satellite of our sun. Another example is our moon is a satellite of the Earth, actually. And yet another example, these are person-made, made by humans, GPS navigation satellites, as well as communication satellites, and Sputnik. So the idea is these elliptical trajectories, or these elliptical orbits, these paths, they are periodic. So, for example, the period is, periodic with some amount of time. So capital T tends to be the symbol for the periodicity, or the amount of time. It's the amount of time it takes before the elliptical trajectory starts over again. So the Earth is at some point in time going to be at its closest position from the sun. That's referred to as the perihelion. And the amount of time it takes for us to wait for the Earth to go out far away from the sun to the aphelion and then back to the perihelion is 365 days, right? 1 Earth year. So the period is the year for that elliptical trajectory. A different example is the moon, or our moon, which is a satellite of our Earth. It takes around, 28 or 29 days for the moon to go around the Earth. So moon's periodicity is about 30 days. That is, the moon's year is 30 days long. And GPS satellites can have different periodicities. Okay, so so ellipses, they are very, very special mathematical shapes. It's not an egg shape. It's not a squished circle, although that's kind of what it looks like. An ellipse is a very, very special mathematical shape, and I invite you to pay very careful attention when you're reading about elliptical orbits to figure out how to draw one. In particular, there are these foci, right? There are 2 focuses of an ellipse, 2 foci. And if those 2 foci sit on top of each other, what you get is exactly a circle. But the relationship between the foci and the ellipse shape is a very special relationship, and that's a very mathematical detail. It's very precise. So long ago, right, in the time of Galileo invented the telescope. But even before then, people were paying attention to the sky. There wasn't that much sort of ambient light around because there weren't big cities with, electric lights at nighttime. So the nighttime sky, if there wasn't any clouds, was full of stars, and you could see quite a lot of detail. And people paid attention to it. If they stayed up at nighttime, they probably didn't have anything else to do, so they're looking at the sky. And if they're inclined to be astronomers or scientists, then those people are going to be very careful about keeping track of what they see in the sky, right? And keeping track from day to day, year to year, and maybe drawing pictures. So there is a lot of astronomy data around, and some astronomers were more could be trusted more than other astronomers, etc. But for example, Isaac Newton had access to astronomy data. And it turns out that Isaac Newton had a lot of influence from astronomy data, in particular the fact that astronomers were saying that the paths of these orbiting objects were ellipses, Newton was influenced strongly to develop laws of motion and a law of gravity that reproduced or predicted elliptical shapes that people saw in astronomy data. And that's really the whole point. So Newton's second law of motion, which is the way we understand the relationship between the net force and the acceleration, right? As well as the universal law of gravity, which is written this way. If you put these two things together, right, so that the force due to gravity is the net force, then it turns out that you also have to invent calculus somewhat as well. If you can do those three things, and Isaac Newton was the person to do it because he was one of the smartest people around at the time, he figured out that this very simple rule of motion, which describes how the acceleration itself is associated with the net force and the inertia, as well as understanding that if gravity had this character, right, if gravity was described by this set of relationships, then you will get elliptical orbits. That's what gets predicted. There was another person that was active back in the day, this guy Johannes Kepler. And Kepler came up with a somewhat different set of rules. First of all, Kepler also had access to this astronomy data. Everybody's talking about it. And it was clear to Kepler that it certainly did seem that the sun was at a focus of an ellipse, and Earth's trajectory is the elliptical shape around the sun as one of the foci, right? So he just said, okay, let's call that a law, because that seems to be the way things are, and it doesn't seem to be changing. Another thing that Kepler noticed, though, and this is very geometric, very diagrammatic, right? Very picture-oriented. He's looking at pictures, right? Scaled out pictures of how the Earth goes around the sun. And he's just thinking about interesting ways to make measurements about the pictures. And this is something he realizes that's very interesting. If you look at, so let me draw a picture of, so here is, let's say this is the sun, and here is the Earth's elliptical orbit around the sun. So the sun is at one of the focuses of the ellipse. And I'll put the other, I'll put the other focus just here, also in this blue color. So these are the two focuses. The sun is at one focus, and the Earth is traveling around on the ellipse. And what Kepler says is if you were to very carefully keep track of how much time passes as the Earth moves, so let's say the Earth is moving in this direction, so the Earth sweeps over, it sweeps out an amount of area, right? So I'm cross-hatching this area that's swept out. And what Kepler discovered when very carefully paying attention to the pictures is that an imaginary line from the sun to the Earth, you can see that I drew an imaginary line from the sun to the Earth, it sweeps out an area, and it's going to be equal to the area swept out at any place in the trajectory as long as you wait the same amount of time. So the idea is let's say for this piece of the orbit, this actually is when the Earth is far away from the sun, it's going to be moving the slowest. So when the Earth is far away from the sun, moving the slowest, let's say that's 1 month of time, the Earth is going to sweep out a piece of pie, kind of like a section of this ellipse, that's going to have the same area as this section of the ellipse where the Earth is traveling faster, but the triangle that's being formed here, it looks like it's formed from shorter sides, so it must sweep further along on its outer edge, right? Yeah, equal areas in equal times. Another thing that Kepler realized, and this was somewhat more quantitative, is so capital T is the same thing as the orbit period that we discussed earlier, right? So the Earth's orbit period around the sun is 365 days. So that orbit period, if you square it, it's related to, or in a sense fixed by, the value also of the average distance that the Earth is from the sun. So what this is saying is, if you could imagine an elliptical orbit of a certain radius, then the periodicity is fixed. You do not get, so for a given radius of orbit, you do not get to choose the period. Kepler's laws predict the period. So the way that you could use this, for example, is what if you want to put a GPS satellite up above the surface of the Earth? Let's say that you want this satellite to live at a distance of 1 mile from the surface of the Earth. So 1 mile from the surface of the Earth has something to do with this radius. And if you want this thing to go around in orbit completely unpowered, except for because of gravity, which is, like the projectile, then you will have a fixed value of the periodicity, right? The amount of time it takes your GPS satellite to make one entire orbit around the Earth. So essentially, Kepler's third law is a very restrictive law that says for any satellite that's located at some distance away, there is a fixed period, and what's interesting is it's independent of the mass of the satellite. So you can see that Kepler's third law here, it doesn't include any stipulation or any issue about how much mass is involved. It could be an entire planet. It could be a tiny, tiny little satellite that you could hold in your hand. And both of them, if they were at the same distance from the sun or the Earth or whoever the central massive body is, they're going to orbit with the same periodicity, the same year. Okay, so these are very interesting laws, Kepler's 3 laws, and they're laws about orbits. They predict the relationship between the orbit size and the orbit's periodicity and time. They predict something about time and area in the second law, and then the first law is just an assertion that ellipses are important, right? That the ellipse is the fundamental shape for orbital motions. Kepler's laws are really, really different in character than Newton's laws. Check out Newton's laws. There's a law about gravities, the forces involved in gravitational interaction, and there's a law about that connects acceleration and net force and inertia. Kepler didn't have forces in this, right? Kepler didn't have inertia. Kepler, So Kepler's and Newton's ways of understanding the same phenomenon, right, elliptical orbits, was very different. And it turns out that, in a sense, actually, they're not that different. That is, you can use Newton's laws to actually predict all of Kepler's laws. And Newton's laws, so I'll just put Newton's laws are more fundamental. And physicists like to have fundamental rules. Okay, so the last piece of this lecture is to talk about energy. So I kind of alluded to it a little bit. Let me just remind you of something I showed you. That the Earth, when it's further away from the sun, travels slower. And when it's closer to the sun, it travels faster. In the same amount of time, it will travel further, right? So that it can sweep out equal areas. And this is an energy issue, right? We're talking about further and closer to the sun, right? So the Earth can be further from the sun or closer to the sun. But when the Earth is further away, it's moving slower. And when the Earth is closer, it's moving faster, right? So what this is an energy statement, actually. It's got to do with energy. And the idea is this. Slower motion is small kinetic energy. Faster motion is really big kinetic energy. And when when an object is further from the Earth, that object has a large gravitational potential energy. And when an object is closer to the Earth, it has a smaller potential energy. And what's going on here is there is a conservation of energy going on. Because the small kinetic energy plus the large potential energy is equal to the same amount on the other side, large kinetic energy plus small potential energy. So, yeah. Another pretty interesting issue is actually, so energy plays out in an interesting way here. This is called the escape speed. And the escape speed is 11.2 kilometers per second. And the point is this, like if you have Earth, let's say you've got Earth, and you take a person who's got a very, very strong arm, and they manage to throw an object and give it at the surface of the Earth a speed. Can you see this is not 11.2 kilometers per hour, right? That's a pretty slow speed. People can jog that, I think. No, I guess you might have to run that really fast. Anyways, but 11.2 kilometers per second, that's a crazy fast speed. So the idea is if you can manage to give this object that speed, right, then what it's going to do is it's going to go away from Earth, and Earth is definitely, Earth's gravitational field is going to bend the path, right? It's trying to make it into an orbit, but instead of ever coming back, it just keeps on going, right? And this is the slowest speed such that the object will keep on going and never come back. The idea is if you go any slower than this, 11.1 kilometers per second, if you throw it there, it's not going to go away and stay away. What it's going to do is finally somewhere really far away, it's going to turn around and come back. That's what's referred to as the escape speed. So 11.1 doesn't do it, but 11.2 does it. This is actually an energy statement, it turns out, but it's sort of beyond the scope of this class to tell you. why, but this is the kinetic energy you need to escape to infinity without any rockets, right? We're talking about satellites and projectiles that do not have any self-propulsion mechanism. So it's just the minimum speed required to start off with, knowing that you're going to slow down as you get further away from the Earth. But the point is you never ever slow down enough to turn around, which is pretty interesting. This circular orbit comment right here is the idea that if you were able to throw a ball along the surface of the Earth at 8 kilometers per second, then what it's going to do is have precisely the right speed to go in circular orbit around just above the Earth's surface. Okay, so that is the lecture.